Have you noticed that this year's heat feels unusual? It's not an illusion. According to the latest WMO report, there is an 80% chance in the next 5 years that new heat records will be broken again. In other words, it may get even hotter. Airports have runways cracking from the heat, and even the Eiffel Tower expanded by 20 centimeters. Meanwhile, in the Arctic, warming is 3.5 times faster than the global average. But while we worry that Earth might turn into Venus 2.0, a more mind-shattering scientific truth emerges. We are actually living in a long ice age, specifically in a relatively warm interglacial period. So when will the next glacial age arrive? To find the answer, we must go back millions of years in Earth's history to feel the planet's climate rhythm and search for clues. Here, you will witness a decisive turning point. It shaped the future of life on Earth and left behind some of the most thrilling legacies. It was the last ice age. This exploration will let you personally experience the extreme conditions that life on Earth had to endure. Over 100,000 years ago, many of Earth's ecosystems were reshaped by massive ice sheets. They were carved by biting polar winds and landscapes smothered in frozen silence. It was a long glacial period, one that lasted thousands of years. As it ended, many iconic species mysteriously vanished, reasons that still puzzle us today. And what we are experiencing now is not Earth's first ice age. In fact, our planet has gone through 5 of them. So what do they all share in common? An ice age is a long-term period of extreme cold on Earth. It can last millions, even tens of millions of years. During these times, vast ice sheets and glaciers cover large parts of the planet's surface. What we commonly call the last ice age began about 2.6 million years ago, during the Pleistocene epoch. And you may be surprised to learn that we are still living within it. Every ice age contains 2 alternating phases, the cold glacial stages and the warmer interglacial stages. In fact, we are currently in the latest interglacial, which has lasted for about 11,000 years. So when people mention the last ice age, they are usually referring to the most recent glacial period, which began 115,000 years ago and ended around 11,000 years ago. Another fact may surprise you. During that last glacial period, global average temperatures were only about 6 degrees Celsius lower than today. Yet even a difference of a few degrees had profound consequences for the entire planet. When we say a global drop of 6 degrees Celsius, we mean a colossal loss of heat energy from all the oceans, land, and atmosphere. During that time, much of Europe and North America was buried beneath 2 enormous ice sheets, the Laurentide and the Fennoscandian. With so much of Earth's limited water locked in these ice sheets, global sea levels were far lower. Land was dominated by cold steppes and dry grasslands. No single factor alone can explain why Earth fell into these vast freezes. But when we examine the planet's orbital patterns, many mysteries become clearer. In the last century, the Serbian scientist Milankovic proposed a bold hypothesis. He argued that long-term changes in Earth's position and movement are powerful drivers of climate. This became known as the Milankovic cycles. He identified 3 orbital variations that together shape Earth's climate. Eccentricity, the shape of Earth's orbit. When Earth is pulled more strongly by the gravity of Jupiter and Saturn, its orbit becomes more elliptical. This cycle lasts roughly 100,000 years. When the orbit is highly elliptical, summers and winters shift in duration and intensity. For example, with the northern hemisphere summer at aphelion, sunlight is about 23% weaker than in January. The result is shorter winters and cooler, longer summers. Obliquity, axial tilt, the angle of Earth's tilt relative to its orbit. The greater the tilt, the more extreme the seasons. This cycle lasts around 41,000 years. When the tilt decreases, seasonal contrasts become milder. Cooler summers may fail to melt winter snows, allowing ice to accumulate year after year, eventually triggering glaciation. Precession, the wobble of Earth's axis. Because of the gravitational pull of the sun and moon, Earth is not a perfect sphere and its axis wobbles like a spinning top. This cycle lasts about 26,000 years. It alters the contrast between seasons, making them either more extreme or less extreme. The combination of these 3 cycles influences the long-term climate of our planet. They are remarkably reliable in predicting major ice ages. But shorter-term changes also play important roles. They can strengthen or weaken the effects of orbital cycles. For example, sudden meltwater surges have been linked to abrupt cooling events, such as Heinrich events, which triggered rapid shifts during the last glacial. This raises a key question. How did life roaming Earth adapt to such relentless changes? What did these creatures look like? How did they survive? Most of the last glacial period took place during the Pleistocene, which began about 2.6 million years ago and ended around 11,000 years ago. The Ice Age was truly an age of giants, and giant is no exaggeration. Some of the largest animals weighed up to 4,500 kilograms. Why did everything in the Ice Age tend to grow so large? One explanation is Bergmann's rule, which states that warm-blooded animals living in colder climates tend to evolve larger bodies because a larger body has a lower surface area to volume ratio, helping it conserve heat. This may partly explain why so many enormous, awe-inspiring species evolved. Being big was a common survival strategy, but the diversity of species proves there was more than one way to thrive. Let's begin with the most iconic of them all, the woolly mammoth. For most of us, the mammoth is the symbol of the Ice Age, a massive, fur-covered giant trudging through the snow, seemingly unbothered by the cold. But in reality, it was not much larger than modern elephants. Fossil measurements show its shoulder height was about 3.5 meters, while some male African elephants today can reach 4 meters. Still, mammoths had key differences. They had thick, double-layered coats, a dense underfur, and a long outer coat. Their bodies were more compact with shorter legs, allowing them to graze efficiently without bending too much. They also had a thick layer of fat for insulation and small, fur-covered ears to minimize heat loss. Despite human attempts to revive them, mammoths ultimately went extinct, but not all at once. One isolated population survived much longer than the rest. On Wrangel Island, in the Arctic Ocean, a group of 500 to 1,000 mammoths lived until just 4,000 years ago, 1,000 years after the Great Pyramid of Giza was built. Next, let's meet stranger creatures, the giant ground sloths. Their name comes from their massive, ridged teeth, perfectly adapted for grinding tough plants. They were bulky, heavy creatures, weighing up to 2 tons, with legs as thick as tree trunks. Protected by bony armor beneath their skin, they looked almost like walking tanks. They could even rear up on their hind legs, using their powerful tails for support, allowing them to reach high branches or defend themselves with crushing force. And then there were the true giants among sloths, the megatheriums. Some reached 6 meters in length and weighed nearly 4 tons. Compared with them, modern sloths are tiny, weighing only a few kilograms. These massive creatures dug burrows large enough to shelter other animals. Scientists believe they may have done this to stay warm or to hide from predators such as saber-toothed cats and giant short-faced bears. To witness these giants courageously facing harsh climates, powerful predators, and shifting landscapes is to marvel at the resilience of life during the Ice Age. Yet the story did not end with these giants thriving in the cold. By the end of the Pleistocene, they vanished with astonishing suddenness. In Australia and the Americas, between 72 and 88% of large-bodied species disappeared. How could this happen? Why? For nearly a century, scholars have debated fiercely. Some argue natural climate change was the main culprit. As the interglacial warmed, sea levels rose, land bridges vanished, and ice sheets melted, disrupting habitats. But this explanation is incomplete. On Wrangel Island, mammoths survived long after the climate had warmed. Another major theory, proposed in the 1960s, points to a new force reshaping the world: humans. And here your journey meets a historic moment, the first appearance of our own ancestors. Homo sapiens emerged around 300,000 years ago in Africa and gradually spread across the globe. They coexisted with the Ice Age giants, sharing the same lands. This raises an unsettling possibility. Were we responsible for driving these giants to extinction? A single human confronting a mammoth would stand little chance. But humans had tools and strategies. By the late Paleolithic, we had mastered advanced spears, atlatls, and hunting techniques. A coordinated group could bring down even the largest beasts. One famous culture, the Clovis people of North America, left behind distinctive spear points. Within just a few thousand years of their arrival, many megafauna were gone. Stable isotope studies show that mammoths made up about 40% of some Clovis diets, clear evidence that hunting pressure played a role. In Australia, the story was similar. Soon after humans arrived, 85% of large species vanished within 4,000 years. And in Europe, another drama unfolded. The Neanderthals, skilled survivors of the glacial environment, disappeared around 40,000 years ago. They were short and stocky, with large noses and strong builds, adaptations for cold air, much like mammoths. Far from brutish stereotypes, they had complex cultures, language, and tools. But against modern humans, they could not endure. Some were outcompete, others absorbed through interbreeding. Today, 1 to 2% of the DNA of most people of Eurasian descent comes from Neanderthals. The last ice age reshaped not only landscapes and animals, but also the destiny of humanity itself. The last ice age brought enormous changes. It forever altered the history of life on Earth. Though filled with uncertainty, many species still managed to survive and adapt, enduring both glacial and interglacial cycles. And now, as you return from that ancient age back to the present, you may feel awe at the sheer diversity of life that once walked this planet. Most of those creatures are gone, their fossils and DNA the only traces left. Yet they continue to spark our imagination, reminding us of a world where, for a time, humans lived side by side with towering beasts and our closest human relatives. But perhaps the more troubling question is this: could such an age return? We are still living in an ice age today, and the next glacial may already be approaching. Scientists point to Heinrich events, abrupt pulses of melting ice that occur about every 10,000 years. They trigger massive cooling, enough to start a new glacial. Evidence shows such events were preceded by sudden disruptions in ocean currents, destabilizing ice sheets. And today, we see similar warning signs. If such an event were to occur, it could plunge Earth back into another glacial period. So when will the next ice age come? Perhaps the answer is no longer decided solely by the Milankovitch cycles. While we fear the return of advancing glaciers, human activity has become another invisible hand, reshaping the timeline. If another glacial were to begin, which species would survive? Would Homo sapiens endure? Or would we, too, be replaced by something better adapted? We are left with haunting questions. In the distant future, what will Earth look like? And who, or what, will call it home?